Uh, Frank, I think we can wait for a couple of more minutes to see if more people can join.
Okay, sure.
Hey, Frank. Hi, Venkatesh.
Hey,
Hi.
welcome, Ocean. I don't know what time it is for you, but thanks for coming.
It's time. It's a good time for me now. It's 9. That's why most days I have to miss because of the time. That's good.
Frank, I think we'll wait for a minute more, then start.
Okay, sure.
Yeah. Yeah, I think we will get started with the introduction. Then, meanwhile, people can join. Hi all, welcome to today's DevDay session. For someone who is attending this kind of DevDay session for the first time, I'm going to brief about it. So DevDay session is a monthly informal event hosted by Sahaj Software. It is meant for developers to share their thought process, experiences, ideas, and perspectives about various technologies they work with. With us today, we have Frank based out of London, who is going to talk about time series analysis. Frank is a principal data scientist and solution consultant working with the Sahaj Software UK office. Over to you, Frank.
Thank you, Venkatesh. Well, welcome everyone. Thanks for joining me today for this DevDay talk on time series forecasting. So as Venkatesh mentioned, I'm Frank Kelly. I'm a principal data scientist and solutions consultant with Sahaj. I've got a background in engineering, including signal processing and data science. And I've had some great opportunities in my career to work on different aspects of time series modeling. usually trying to help businesses make informed decisions based on their data. So today, I'm going to share my experience with you as we explore the world of time series. Time series data is a large part of the world's data, and understanding how to analyze it and make predictions can have a huge impact on many different industries. So hopefully by the end of this talk, you'll have an understanding of the basics of time series forecasting, including some common techniques, some best practices. Can't promise to show you everything in the time, but we'll see what we can do. If you're super brave and you don't mind installing lots of dependencies, then you could try following along in the actual repo here, because we're going to do a sort of a live coding session a bit at the end. I'll take you through the code. So if you want to join in, please scan the QR code. Okay, next slide. So we're going to cover the importance of time series forecasting, basic techniques like moving average, ARIMA. We're going to delve into some advanced techniques, just describe them and talk a bit about how they work. We're going to look at metrics, how to compare different methods. We're going to do a bit of hands-on playing around with some real time series data. And then I'm going to summarize the best practices and tips, and then we can have some questions and answers. So, but first of all, a quick quiz. If you scan this QR code, or you can just, I just present this. If you go to menti.com on your mobile and you just type in this code, or even on your laptop, I just wanted to know the audience level. And that's good to see that based on a proportion of 5 people so far, they all seem to be beginner level, which is good. That's kind of how I was pitching it. So there we go. Oh, some intermediate people coming in. So just to get an idea of the audience makeup. Excellent. And then the next one. What's your main reason? Is it to understand the basics of time series forecasting, or to explore advanced methods, or to understand the differences between different methods? Or is it to apply these methods in your own work or projects? Okay, so we've got a bit of a mix. But generally, people will understand the basics and a bit on advanced. Okay, it's good to know. And which of these forecasting techniques have you used before? Just select any that apply that you've actually had to go with. Interested to see. Okay.
मैं सोया हुआ था.
Okay, so we've got a lot of love for linear regression. That's good. Excellent. Okay, and some people have dabbled with LSTMs and transformers. That's brilliant. Thank you. Okay. Right. So, if we go back to the talk, let's dive into time series forecasting. So, we'll begin with an overview of. I think somebody needs to mute out there. I'm not sure if Venkatesh, you can mute people, or if they can.
Yeah, I did that. I think you need to unmute, Frank.
Go ahead, Frank.
Yeah, I'm unmuting now. Sorry, I got muted as well. It's
Yes.
Thanks, Venkatesh. Very careful. Yeah, that's good. So we're going to give an overview of time series data here. So its components and its importance across different industries. So basically, a time series is a collection of data points that are indexed in chronological order, usually taken at regular intervals. And this allows us to observe and analyze changes over time. This type of data is particularly useful to understand trends, patterns, and relationships in data as they evolve over time, which can help us make informed decisions and accurate forecasts. So, as I've said, time series data is quite ubiquitous and can find in nearly every aspect of human life. Even my heartbeat is a time series, which is slightly elevated because I'm beginning a presentation, but still, it's time series data. Majority of domains you can think of will generate vast quantities of time series data. So to provide a bit more detail about time series, let's consider some sort of basic characteristics. So first thing to think about is, I mean, you can break it into these four main elements. First thing to think about is trend. So trend is really a long-term movement or the direction of the data. For example, gradual increase in temperature, global temperatures over several decades, as you can see here. That represents a trend. That's a very long trend, so over 100 years. But then you could also look at shorter trends. So you can look at 15-year trends. So post World War II, you've got a drop in temperature, and then you've got a flat line, and then in the 70s, things start to hot up in 15-year chunks. So you can determine the length of time over which the trend occurs, but nonetheless, you start to see trends in almost any data set. The next thing to think about is seasonality. It's a very important component. So this is referring to the regular fluctuations that occur within a specific time frame. Think of daily, weekly, monthly, or yearly. For example, retail sales will exhibit some seasonality. So you've got higher sales during the holiday season and lower sales in other months. So you can, if you're looking at, this is aggregate retail sales for bars and restaurants, you're seeing that due to the weather, due to people's behavior, due to society, we tend to shop or eat out at certain times of the year. So you get this regular pulses in the data. Something else is irregularity or irregular fluctuations. So this component of time series data is really referring to random variations. You cannot attribute them to trend or seasonality. They're more like unpredictable events, like natural disasters or sudden shifts in the market, for example, in the stock market. And this is both really because this is a sort of something happened in March 2020, and it was a big event, which we know. And it caused ripples, not just in the stock market, but across practically every part of our lives. So you can see this jump in the time series that isn't really a trend or a sign of seasonality. It's just an unexpected, seemingly random event. Then you've got cyclical patterns. So these are recurring patterns. They don't follow a fixed periodicity. Examples of these are economic cycles. So you got a period of growth and recession. So in the UK, economy grew very well in the 1980s, and then suffered a big recession in the 1990s with a house price crash and the rest of it. And then we had more stable growth. This graph is perhaps confusing because it's showing growth rather than absolute value of something. So just bear that in mind. But you're seeing these different periods of growth and recession that are not really seasonal. They're just sort of much longer term cycles that go on. So what we're looking at on the right is a plot that demonstrates what is known as seasonal decomposition. So this is the original data set at the top. This is actually numbers of airline passengers for an American airline in the 1950s. So and it's a commonly used data set in time series analysis courses. But when you break it down, you get your trend. So you're seeing a nice increase in passengers and you get your seasonality. But if you look at the seasonality, it's increasing in amplitude. So it's a multiplicative seasonality. And then you've got this residual, which is events that, these are your irregularities occurring that are part of the data set as well. But they're very subtle, so you can't really observe them even when you look at the main data set. So some examples of time series data: stock prices. We've talked about financial markets generate huge amounts of time series data. The stock prices, for example, are recorded at regular intervals, usually daily. Electricity consumption is another example. So this is the energy demand in megawatts in Connecticut, in the United States. Weather data. Time series data is used in meteorology to record and analyze meteorological observations. So you've got temperature, precipitation, wind speed. This is London temperature. A bit cooler than some of the cities that some of the viewers are based in at the moment. We've got sales figures. Companies often track their sales figures over time to identify trends, seasonality, and the impact of marketing campaigns. So here you can see the impact of different marketing campaigns and launches of products for Apple between 2008 to 2016. And let's see, overall, we'll do a quick sweep of many industries and see what they use time series forecasting for. So finance, they'll use it to make predictions on stock price behaviors, we mentioned, but not only stocks, also bonds, also macro factors, many different financial indicators. And with those predictions, they can perform things like portfolio optimization, so they can predict different assets in the future and help you rebalance your portfolio. Something important is foreign exchange rate forecasting. So companies, companies and individuals can manage risk, make better decisions related to international transactions. Electricity and energy. Accurate predictions of electricity demand forecasting enables utility companies to optimize their generation distribution, ensuring a reliable supply. So, for example, they're aware of peak demand periods and they can adjust power plants accordingly. Renewable energy. So time series forecasting can be used to predict the output of renewable energy sources, such as solar, wind power, based on weather data and historical patterns. This information can help the grid operators sort of manage the energy storage. Then you've got climate and weather. So weather forecasting, you've got temperature, pressure, humidity, and many other meteorological variables. They're used to make short-term and long-term weather predictions, which is crucial for agriculture, transport, emergency planning, and air quality management. Climate change modeling. By analyzing some historical climate change data, time series forecasting can help scientists develop models to predict future climate events, thereby informing policy around decisions around climate and strategies. In healthcare, you can help predict epidemic disease outbreak. You can predict the spread of infectious diseases, so you can allocate resources more efficiently. Monitoring of patients is a big area, so you're continuously monitoring vital signs, heart rate, blood pressure, as I mentioned. It generates time series that can be used to predict patient outcomes. Social studies even, so you can look at population growth, migration trends, other demographic trends. It will inform policy decisions related to urban planning and education. Economic forecasting, so looking at unemployment, inflation, can predict future economic trends, so you can inform monetary and fiscal decisions. So in this country, they're adjusting the interest rate in the central bank, but they're looking at their forecasts before they make any decisions on that. And then you've got astrophysics, completely different, but still using the same idea. So tracking objects, distant objects, using time series, so such as stars, planets, asteroids. And then you've got detection of astronomical events, so looking for supernova, solar flares, gravitational waves. So these time series analysis plays a part in that. Self-driving cars as well. You might do traffic forecasting the time series. You might do you'll be definitely doing sensor data analysis. So you'll be looking at lots of different time series data from LiDAR, radar, and cameras and the rest of it to help the car's decision making and ability to anticipate and react. So all these examples show the critical role that time series forecasting plays in many industries, many applications, contributing to risk management, resource allocation, and decision making. So now we'll go and look into some actual, we'll actually look at time series data and talk about the specifics. So two main types of time series data we usually consider as data scientists. So univariate would be some kind of single variable over time, just like a stock price, like you were looking at before. Traditional methods can be applied, and I'll talk about some of those to this. Multivariate time series, on the other hand, are when you have several variables you're observing over time. For example, you might have air quality data, you might be looking at nitrous oxide and PM2.5 and temperature and combining many different series. So when you're doing multivariate time series modeling, you'll be capturing relationships between these variables, and that's certain and more advanced methods will come into play. I think in this presentation, we're mainly focusing on a univariate time series. Let's jump into some core foundational forecasting techniques. So simple moving average is a technique. It's been used, since the early 20th century, initially used to analyze agricultural commodity prices. So it's very basic. So it just calculates the average of a set of data points over a given period. It literally is the average. Then we get a bit more technical. So in the 1920s, we have the weighted moving average. So this assigns different weights to data points. More recent points receive more weight, so that your prediction is more responsive to recent changes in the data. And this was further developed in the 1960s to incorporate an exponential decay factor. So it makes it more responsive to recent changes while still accounting for older data points. And then something called exponential smoothing was invented in 1956 by Brown and Holt. So the idea is it's a technique for, again, smoothing a time series this time, but by giving more weight to recent observations. So single exponential smoothing, or SES, is the original method, and it's suitable for time series data that doesn't have any trend or seasonal component. And you can see the smoothing factor in there. Then you've got double exponential smoothing, known as Holt's method, developed by Charles Holt, and it extends the single exponential smoothing by considering a trend in the data. So this is your HBT, so that's your trend component. And triple exponential smoothing is the next step onwards because it considers, beyond Holt's method, it considers trend and seasonality in the data. So you can look at fairly complex time series using this method, and that's also known as Holt-Winters method. So there was a big if you notice all these dates are close together, there was a big surge in interest in time series forecasting in the 1950s and 60s because of the rise of computers, really, because it made it possible to analyze large data sets, perform complex calculations more efficiently. Another core technique is ARIMA. So this was developed in the 1970s, and it's got three components. So it's got autoregressive, which as it says, it molds the dependency of a data point on its previous values, whereas the moving average component models the relationship between a data point and past forecast errors. And in the middle, you've got this integrated component, which makes the time series stationary, basically differentiates it. So it helps to eliminate any trends and seasonality. And it's defined by these three terms, which is the order of the autoregressive term, the degree of differencing, and the order of the moving average term. So these two, Box and Jenkins, were very influential in the development of modern time series analysis. And George Box was actually not only a renowned statistician, but he had a sense of humor. And in a famous quote, he said, essentially, all models are wrong, but some are useful. And there he's just talking about the inherent limitations of models, because they really are simplifications of reality. And he acknowledged, although models can't be entirely accurate, they still provide valuable insights into complex processes. So, a bit of a summary of the advantages of these approaches mentioned. The simple moving average is very simple to use, as you saw. It just smooths fluctuations in the data. As a result, it reduces the impact of outlier impact and can help identify seasonal patterns. The downside is it is literally limited to past values, and it ignores any complex relationships in the data. It's not really suitable for complex or non-stationary data. So the single exponential smoothing is also simple, easy to use, and it places more weight on the most recent observation. So it's even more responsive to recent changes. And it can be extended to quite complex models, such as the Holt-Winters one we discussed. The downside, it really is for short-term forecasting because it relies on current patterns. And again, doesn't handle sudden shocks in the data. ARIMA, on the other hand, captures both linear trends and seasonal fluctuations in the data, and it can be extended to enhance its versatility by, into a ARIMAX, which incorporates external variables, and a SARIMA, which adds seasonality. So you can apply it to complex time series data. On its own, just pure ARIMA, it does need a minimum number of observations to be effective. It assumes really that the time series is stationary, so you do need to transform it beforehand. And it also assumes linearity. May not really work well for long-term forecasting or any kind of complex non-linear relationships in the data. And it does require a bit of expertise, and it's a little bit time-consuming to select, as you'll see later on. So some advanced techniques we'll look at. State space models, they date back to the 1960s. So these are sort of general class of dynamic models. They describe the evolution of a system through a set of latent or hidden states. And the most widely used state space model for time series forecasting is the Kalman filter. A nice feature of these models is that they can handle missing data and noisy data and multiple sources of data, and they can easily account for complex patterns such as trends, seasonality, irregular components. So the diagram you see on the right shows how a Kalman filter works. So it's got this predict step, which is predicting the next step of the system, state of the system and its uncertainty, using the previous state estimate. And then this update step uses the observations or the measurements to refine the predicted state estimate and reduce its uncertainty. And so the filter just alternates between these two steps, producing the next state based on the previous state and available what it can observe, and then updates the prediction using new observations. So this is a very mathematically optimal way of combining predictions and observations, and it works well, reliably, even when the underlying system measurements are very noisy. And it was used to actually, the first major usage of it was in the Apollo space missions. It enabled navigation to the moon, despite very noisy sensor data, and was a great success. It was probably the key to one of the key parts of the moon mission. Its benefits, therefore, are, as I've mentioned, can handle many sources of data and allows a combination of many different data sources, which can be noisy. Then another advanced technique are recurrent neural networks. These were introduced in the 1980s. They're specifically designed for processing sequential data. And the key aspect of this type of neural network is it has a hidden state. So normal feed-forward networks don't have this hidden state. And it's here on the diagram shown as A. And it acts as a form of memory. So the hidden state allows a recurrent neural network to capture patterns across different time steps in the input data. So you have xt, that's an input, fed into an RNN, and the output is a hidden state, which is h of t. So the hidden state is also fed back into the model itself, so allowing the network to remember and learn information from previous time steps. So this is a loop structure, so you can capture, over time, you can capture complex patterns of dependencies, which leads to better forecasting accuracy. So the advantage of an RNN, it can model complex non-linear relationships. So it's good for where basic methods might struggle. And it addresses some limitations. It can handle long-range dependencies. And it can also be combined with other techniques to further enhance the performance. And it's been used in many domains, particularly natural language processing and speech recognition, and even generating Harry Potter text. So this is text generated by an RNN, but it looks quite realistic, mostly. So RNNs have been sort of improved and developed into LSTMs. So this is a type of RNN designed to overcome something called the vanishing gradient problem. So when you have deep neural networks, the gradients of the loss function with respect to the weight become very small during backpropagation, and it leads to hardly any updates in the weights. So it's difficult for the network to learn. So LSTMs overcome this. They have three key components: the input gate, the forget gate, and the output gate. So this gives like an overall cell state, and it allows an LSTM to store information over longer periods and capture long-range patterns in the data. They're very powerful in time series forecasting because they can learn and run patterns that occur over varying timescales. So they're suited for tasks where relationships between data points are not only based on their immediate neighbors, but also on data points much further in the past or the future. And they address the challenges of basic methods and standard RNNs by being very effective in capturing these dependencies and handling the relationships. So another advanced technique, fairly modern as well, Profit, developed by Facebook. It's what's known as an additive regressive model. It's an open source forecasting tool designed to handle time series data with missing values, outliers, multiple seasonalities. It uses a decomposable model with additive components. So you have trend, seasonality, and holidays. It makes it quite flexible and quite easy to interpret for humans. And the additive components are all custom functions, which are considered to be more effective than normal functions. So it addresses kind of a lot of the challenges of the basic methods by being robust to missing data, outliers, and handling multiple seasonalities more effectively. And it works very well with day-wise date data, if you've got day frequency data. And it's been used by many organizations already. Finally, the final sort of advanced technique I'm going to discuss is transformer-based models. So these were also introduced in 2017, and they've become, you could say, the de facto choice for sequence-to-sequence tasks, especially in natural language processing, which is what they were developed for. So it's not a recurrent architecture. It's actually using a self-attention mechanism to process sequences in parallel rather than sequentially. So you get a hugely more efficient computation, and it's been applied to time series forecasting as well. So the main part of the component, the main component of the transform model is this attention mechanism, which allows the model to sort of weigh the importance of each input data point relative to other data points when it's making predictions. And it can, the main architecture consists of an encoder and a decoder, which each have multiple layers within them. And each layer contains these attention mechanisms and also feed-forward networks inside, which are combined with positional encoding, which captures the sort of sequential nature of time series tourist data. And then something called layer normalization is used to sort of stabilize the whole training process. So one of the advantages is the ability to be highly parallelizable and scalable. So you can handle very large scale time series effectively. And so it really addresses the challenges of the basic methods by handling this long range data dependencies and complex linear relationships effectively, but just like RNNs and LSTMs, but way more computationally efficiently. So, and they've been shown to be state-of-the-art performance in many tasks. In NLP, we're seeing it with ChatGPT and also in computer vision, and more recently in time series forecasting. So just an overview of the techniques there. State space models, it's all about multiple inputs that are very noisy. It's very good if you've got a system where you want to incorporate many external factors, because you've got uncertainty estimates, confidence intervals, and you've got a very reliable model underneath for real world systems. Recurrent neural networks, one of the first proper attempts to use a neural network to capture long-term dependencies, looking at sequences. And they can model linear and nonlinear relationships. So it's a wide range of forecasting tasks. Your LSTM or long short-term memory resolves a problem with RNNs, and it just models long-term dependencies while preserving short-term memory. Profit is easy to use, requires minimal time series expertise. It's a great benefit. All of these techniques require significant expertise and knowledge about the model and how to train them and the rest of it. Whereas Profit is pretty much plug and play. It's got pretty good diagnostics for looking at the weaknesses of the model and confidence intervals and the rest of it. Transformer-based models are really the state of the art at the moment. And one of the features is they can handle variable like time series data. And again, they model the complex relationships between inputs and outputs in a system. So they're a great option at the moment. How do we evaluate all of these models? Well, it's important to use metrics that measure the accuracy of predicted values relative to the actual values. So these just help us understand how well a model is doing. So mean absolute error is quite a commonly used metric, and it's represented by this formula. So it's just ensuring the absolute, just taking the sum of the predicted values versus the actual, and then making it absolute. The root mean squared error is another very commonly used technique because it's quite good because it penalizes larger errors more than smaller ones due to the square root factor. And so it's calculated the square root of the mean squared error. Oops. R squared, which is also known as the coefficient of determination, is a metric. It's used to evaluate the goodness of fit of a regression model. And usually it ranges from 0 to 1, where 1 indicates a perfect fit and 0 indicates the model does not explain any variation in the dependent variable. But it can, if you train a model on separate data sets to the one that you're testing it on, often you can get negative R squared values. It's quite a common occurrence. So bear that in mind. Mean absolute percentage error is quite commonly used as well. It's good if you're evaluating different data sets on different models, because obviously you've got your units of measurement, and if you're looking at absolute error, it's going to vary depending on which units you're using. The mean absolute percentage error is a good way to look at large numbers of different data sets with different units when you're checking a model. The Bayesian information criterion is another metric, not necessarily used directly for comparing the outputs of the model, but you can use it to compare different models. So what it will tell you is the relative quality of a statistical model, the balancing the goodness of fit with the model complexity and avoiding overfitting. So a lower Bayesian information criterion indicates a better model fit with appropriate model complexity. And that's the formula there. So enough of the theory. So now we're going to have a go with a live demo. Is everybody still following so far? I think that's a yes.
Hey, just wanted to add that if anyone has a question, please feel free to ask.
Yeah, please. Okay, I don't think there's any question, unless you had a question, Venkatesh.
Yeah, sure. I think we can proceed.
We can move on. Okay. So let's start off with a real world data set. So this is you may not be used to this dark background, but this is a Jupyter notebook running in Visual Studio Code. So what I'm going to do is load in some data and a couple of libraries. I'll explain as we go. We just want to have a look at the data to start with. So we're going to start off with some energy demand data.
Hey, Frank, one request. Is it possible to zoom in slightly?
Yeah, sure. Any better?
Yeah, I think this is great. Yeah, thanks.
So first thing we're going to do is going to plot the data. So I've written a small function to just plot the data that we've loaded in. And actually, doing a few things in the background, but that's not important right now. So this is what the data looks like. Just to prove for running live, I'll run a few cells. These have been pre-run as well. So this is energy demand. This is an example of a real world time series data set. So this is kind of typical, although this is a very nice data set, you can see. There's no holes in it. And it's not been scaled in any way. This is how it is. So this is actually an open data set, but I understand it's real data from Connecticut in this case, but you can download from many different American states and look at the energy demand over a certain period. To look at the data itself, we're using a library called Pandas. So some of you may be familiar with that, where we can just look at the top of sort of Pandas data frame, which is a special object. And you can see you've got some float values in there. And you've got an index. This is a very basic, this is what a time series looks like. We're looking a bit at the data, what is in the index. And what you can see there is that it is weekly data, because you're getting once a week, and it seems to be on a Sunday. On a Sunday. So that's good to know. You can actually take a look. What does weekday equals 6 mean? Well, as we've answered, it means assuming weekdays are numbered 0 to 6, it's a Sunday. So every day in that data set is a Sunday. But the data in this case is actually averaged for the whole week, but just recorded on a Sunday in that index. So that's good to know. This may help us later if we're trying to spot missing data and the rest of it. So one thing we want to do is to split the data into training and test sets. So if you're going to do any kind of forecasting, you need to train your model. And if you really want to test your model, you don't really want to train it on the whole data set, because then your model will know the answer effectively. So you want to split a proportion of data set to be tested on. So you just split it up, and here I've arbitrarily said the first 80% of the data will be training and the last 20% will be testing. You can run that, and it's created the test data and the train data for me. I'm just using indexes. One quicker way to do this is to use scikit-learn library, which does it automatically. One thing you don't want to do is to shuffle the data. I mean, in other machine learning problems, it's quite common to shuffle the data because you want sort of a random sample of the data. If you shuffle time series data, which I've seen done before by data scientists, then your model is kind of, it's a bit like if it's Wednesday and Tuesday and you're predicting Saturday, but you already know what the answer is on Sunday. You're kind of cheating because the model is seen into the future, and it's a very odd thing. So just make sure if you use these libraries, that automatically make sure that you're not shuffling data, for example. So the output really is a training data set, about 600 data points here and about 150 for testing. The next thing we want to do is perform some exploration of this data, some exploratory data analysis. First thing to do is to think about stationarity. So what does that mean? Well, it's quite an important concept, because if a process is stationary, a perfect stationary process is sort of white noise. Its probability distribution does not change over time. So the mean of its distribution does not change and the variance does not change. So how do we check for stationarity? Well, we use something called the augmented Dickey-Fuller test. And if we run it on our training data in Python, we can use this method called ADF, which nicely calculates the Dickey-Fuller test. It's telling us that the process is stationary. So if I run it, it says, is this training data set? Because the p-value is less than 5%. So the training data is stationary in this case. Okay, that's good to know. So effectively, there's not too much variation over the period of the training set in the mean or the variance. So next, we want to do something called autocorrelation plots. So autocorrelation is effectively how correlated the time series is with itself. If you were comparing it to a version of itself slid along by a window. So it's just a sort of correlation with itself over time if it was sliding past a version of itself, if that makes sense. What you need to do, though, is determine how many lags you want to do this plot over to get useful information. And here's a sort of a cheat sheet. If you have daily data, you want to use around a month. Weekly data, you probably want to use at least a year. Quarterly data, about 2 years. Monthly data, 2 years. Annual data, you probably want to look at what's happening over a decade. And depending on your domain as well, I mean, this is all very arbitrary, but it's good to have some kind of guide, because otherwise it's all very confusing. If you're looking at daily stock price, then you probably want to use 20 to 30 lag points to get your short-term trends. If you're looking at climate months, you want to look at long-term trends in temperature, for example, is 30 to 50 and so on. So another question to ask is, do we have enough data points? We probably need 2 to 3 years worth to really sort of run a decomposition, which we'll do later. We've determined that the data is weekly. So we're going to plot 52 lag points. So we'll use this function called plot ACF, which plots the autocorrelation function. So this is a better, so autocorrelation is a correlation between a variable and a lag of itself. And then a partial autocorrelation is a correlation between a variable and a lag of itself that is not explained by the correlations of all shorter lags. So plotting those two, so at the point where the value crosses this blue shaded part is something called the best value for the auto regression. I'll explain it a bit later on because we're going to apply a bit later. So in general, if you look at sort of patterns observed, if you see in the autocorrelation function, if you see a general gradual decline, then you're pretty certain that there's an autoregressive component in the data. And if it drops off quickly and remains near zero, then there may be a moving average component. If it's oscillating, it's telling you there's probably a seasonal component, which we can see very clearly here. And on this diagram, the partial autocorrelation function, if there's a sharp drop off after a certain lag, then there's an autoregressive component equal to that lag. So that's telling us 0, 1, 2. So after 2, between 2 and 3, there's a big drop. So that's good to know. So then something else you have to look at is seasonality, as we discussed. So, but how do you describe the seasonality? Is it additive or multiplicative? So are you just literally adding absolute values to the trend? For example, if you're selling a product and your sales increase by a fixed amount by 200 units during summer, and you normally sell 1,000 units, then that's additive seasonality. Whereas it's multiplicative if you have sales increasing over time, but you're getting a percentage increase. So say you 1 year you sold 2,000 units, but in the summer you're selling 2,400. It's the same. It's more of a percentage increase if it was 20%. So I hope that makes sense. So this is helping us understand the type of seasonality, and you can observe it in the data itself. So you can see sort of a constant amplitude, and you can see an increasing, or you can see an increasing amplitude or decreasing in multiplicative. And you can see different types of fluctuations in the data. So you might get some kind of exponential change for multiplicative, or you might get some, or just a constant fluctuation or linear change. You can't really determine whether a model is additive or multiplicative automatically. You can't really determine it. You can try fitting both types of model and then compare the model performances. So what we'll do now is we'll actually just have a go at that. So we'll use the stats model seasonal decompose method, and we need to set a value called period. It really specifies the periodicity of a seasonal component, like how many observations in a given season would you see? So quarterly, you're going to see 4 over a year. Weekly, you're going to see 52 over a year. So it's the periodicity of the seasonal component. That makes sense. And you can actually deal with non-integer seasonalities. For example, if you have a pattern in your data that occurs every 12.5 months, you would actually have to set your period to be 25 to capture the full pattern. So you need to capture it over 25 months. So what we could do is decompose our time series. So if we run this, a library called seasonal decompose, we're going to assume the model is additive. We're running it just on the training data. It actually breaks down very quickly our time series data into these different components. So you've got the original, got some kind of trend going on. It's a bit jittery, but you've got a nice clear seasonal pattern coming through. So this is, sorry, I've skipped on to the next one. There's your seasonal pattern coming through. So it's additive because you can see like an absolute increase. So if you literally add these components together, you will get this top one. Okay. Your residual, what's left in the data is this noise here. And it's all the things that are, like I said, that are not really explained by the other two components. If you run a multiplicative model, so you're assuming that there is a gradual change in the seasonality. This is what a multiplicative model looks like. It looks pretty similar, to be honest, but you'll notice the seasonal and residual components are a decimal value or percentage rather than absolute values. So these are applied in a multiplicative fashion to the trends to develop the original data. So a more advanced is to use STL, so seasonal trend decomposition using lowers. I don't have time to explain it, but it takes more arguments. It's considering the number of observations in each seasonal period, and then you've got the numbers of observations in a complete cycle of seasonality. So if we run that, it's giving us a nice breakdown, once again, with a much smoother trend and a very clear seasonal signal and a somewhat reduced residual component. So these are all ways of performing seasonal decomposition. We've had a look at a data set there. So let's move on, if nobody has any questions, to actually try running a single model on a data set. Oops, so there we go. So I would import a few libraries, modules. I will load in my data set as before. I'm going to split it into test training and test set. And I'm going to start to train a basic ARIMA model. So the first thing we need are the model parameters. So as I mentioned, these are the P, D, and Q values. So earlier, we looked at these two plots, ACF and PCF plot. And with the best guess, we determined that P was about 6. We saw that the data is stationary, so there's no differencing required. And we saw that Q is 2, because you've got this sudden drop off in the ACF around 2 lags. So we can take these values and we can use them in our model, because we've done a sort of mini analysis, and we're now using our knowledge from this analysis to feed into the model. So the first thing we do is we use a module called stats models, and it's got a time series analysis module, and you can load in the ARIMA model from that. So you literally feed it the training data and your 3 components that you've worked out, along with a couple of other arguments, and you fit the model. That was pretty quick. So what we can do now is we say thank you to the model that it's trained on the training data set. Can you actually predict forward into the future? That, you know, part of the data set we've never seen, the model's never seen before. So the model will happily do that. So it's actually predicting there, so you can see the values. Again, the same frequency, but just continuing. If we plot the predictions against the actual values, we've got our prediction. So this is the output of an ARIMA model trying to predict energy consumption. As you can see, it's not doing a great job because ARIMA on its own, it doesn't really know about seasonality. And we haven't performed any differencing on the data because the data was stationary. So we've reached the sort of limitations of a pure ARIMA model. But in the defense of the model, it's giving you sort of an average, eventually an average value that might coincide roughly with the average, but it's not going to give you enough information to produce week-on-week predictions. So we can do better than this. So let's try and find the best values for these parameters, these three values, rather than trying to work them out from a graph. And let's also, because ARIMA doesn't really work well with seasonalities, we could use this wrapper library called STL forecast that actually can take the ARIMA model and ask the ARIMA model to only perform predictions on the residual. So it can take out these other two components and just ask the ARIMA model to just work on this part. And then these components can be added in afterwards. So let's give that a go. So excuse all the messy code, but these are parts of another code module I've written, so I'm just bringing it together here. What we'll do a sort of a grid search. We'll go through different PDQ values and trend values, which the forecast needs. And different types of trend. And we'll play with different values and we'll see if we can get a better result. So if we run that through, if we run that in real time, we'll see if that runs. It's going through. It's going to take a little bit of time. I can leave that running. But then once we've got the best fitted model, we can so we're recording them from this function to get the best values. We'll feed them into our forecaster. So the forecaster takes the training data, takes the model, and gives the model its configuration and needs to know the period, 52 weeks, and we'll get the sort of best fitted model after our grid search is completed. So once that's happened, we can then run a forecast and create a prediction data object. And the prediction is giving us, this is a slightly more advanced model to give you a forecast of actual value and then a mean, and then confidence intervals, upper and lower confidence intervals. And we can actually plot the output. So this is plotting us alongside the training data. It's plotting the test data in crosses and it's plotting the prediction to the right. So I think you'll agree is a much better prediction after doing a grid search and after relieving the model of the seasonal and trend components. So letting the model focus on the residual. So that's quite a nice prediction. Not amazing, but it's a good start. So let's move on to some challenges we get with data. Unless anyone has any questions at this point. Okay, let's carry on. So one thing we want to do is look at what sort of problems do you get with real world data. Let's look at data from instead of electricity consumption from the States, let's look at pollution data from India. So one thing you might have with time series data is missing values or unevenly spaced timestamps, or data sets of different lengths that you're trying to compare. So what you can do is use either interpolation or resampling. We could try a slightly more advanced technique called multiple imputation by chained equations, or MICE. So it's an advanced statistical method. So it performs imputations by observing a multivariate time series, and it's actually using a regression model to try and work out values in the missing data, and then sort of averaging the results. This is good when you've got a large number of missing data, as I'll demonstrate. So in Ahmedabad, we've got we load in the data. We've got pollution measurements. So we've got PM2.5 with very small particles, PM10 also slightly larger particles that get stuck in your bloodstream, very bad for you. And some other measurements. So carbon, we've got sulfur dioxide, nitrous oxide. These are all not really good for you. So we're measuring all of these on the raw data is daily, actually, in a number of Indian cities. So we can actually plot to see what they look like. Now, Ahmedabad, it's plotted the data, but there's just huge amounts of missing data inside there. So what do you do with that? So one thing you can do is, plot a few different metrics, but there seems to be a common problem. Regardless of which metric you choose, it looks like either the sensors were turned off at that time, or the data got corrupted, or who knows, many different reasons why there's holes in your data set. So one thing you might want to do is interpolate. And you could do a linear interpolation. So if I run this code, so I can get a linear interpolate. Oh, I need to run some earlier code.
Suman has a question, I think. Please go ahead, Suman.
Yeah, hi,
Please jump in.
Yeah. I just wanted to ask you, like, in your experiences, like I am also dealing with time interpolation. What interpolation works for you? Because as far as I understand, like in case of a data interpolation, we have different type of interpolation, like padded, linear, time. So what do you think? Which one works well for your model generalization performance? Thanks.
Right. Well, linear interpolation is good up to a point. I mean, it's good if you've got very short periods of time missing. But you can try other. I think there's something like cubic here. Does it let you do that?
Time and padded.
It's a bit risky because it's a bit wacky. You're probably best to stick with linear there with using that approach. But I think you might want to consider a more advanced approach if you've got lots of time series, which I know from inside information that you do have lots of time series, Suman. So you probably want to try something like this multivariate imputation by chained equations. So if I run that, it just takes a little minute, but it's going through, this is some functions I've written. So it starts to look at the data. If it's got a certain amount of missing variables, it starts to do advanced imputation. So then it actually cleans up your data set. It gives the best guess based on a number of factors, and it gives a sort of more realistic set of missing data for you.
Which one did you use right now?
Sorry? This is called MIC, multivariate imputation.
Okay, thanks.
By chain equations. If you
if I can
Go ahead,
say something, sorry,
Sure.
Vish. So just a continuity of that. See, Suman, my view is it all depends on the nature of the data. If you think the missing data, there is already some sort of a polynomial trend in the data, and that polynomial you can choose. And if you are totally using automated method, then you can try out different polynomials like linear, second degree, third degree, fourth degree, like, whenever the error is less. So that is the right thing. So there are two ways of doing. One is manually you can verify the data and choose the right polynomial degree and then do that. Second is if you are going automated method, you keep different polynomials you can try, and whichever is given the least error, that will get. That's what I think so. But my 2 cents.
Sure. Thanks.
Sorry, Ocean, I interrupted.
Yeah, actually, I was going to say exactly mostly the same point. that it's majorly dependent on the data distribution, data smoothness, the dimension of the data. And you should also look at what is your target, right? If you're looking at higher complexity kind of a problem statements, are you looking at improving your accuracy? Sometimes you also need to see in context that an extrapolation might work better than an interpolation. So it is very problem statement specific. It is very target objective specific. It is also a lot what Ravindra pointed out, that data specific. What is the nature of what is the smoothness of your data, and what is the dimension of your data, what is the distribution of your data? All those kind of play a factor on what kind of interpolation that you want to choose. Yes, a similar point as Ravindra, just adding onto that.
Yeah, just to add to that, if you just have a univariate distribution, you can't use this multiple chain equations approach. You will be limited to just different forms of.
To say this only.
Yeah, you're limited to different forms of interpolation, unfortunately. You have to think out of the box. If you can introduce time series that are very close to the main data set you're trying to fill in, then you may be able to get away with it on the same time scale and the rest of it, like Ocean said, which have complex relationships, then you might be able to do something like that. But yeah, it depends on the problem. So something else you can do is just simply resample the data. So when you resample the data, it just ensures that the data is at a regular frequency. And here I've resampled the imputed data, so you kind of see a fake version of it, but it has a double feature in that it removes extreme values as well. But obviously, the more you remove from the data, it brings its own risks as well. And you've got to look at the problem, the nature of the sensors and the rest of it, and how reliable is your data. So further on that point, often we're looking at removing noise and outliers. So if we look at another Indian city, if we look at Hyderabad, the data here, it's got a little bit of missing data, but not too bad. But what you're seeing is extreme values early on in the time series. So going up to 500 micrograms per cubic meter. And then suddenly in 2017, you don't see these spikes onwards. So that would lead you to think, either has there been a change in the way they're measuring? Has there been, it could be some kind of policy enacted banning certain types of vehicles in Hyderabad. But yeah, you would look at the problem. If you knew that it was maybe a change in sensor supplier or something, then you might want to remove these outliers, because you're really trying to predict, thinking about the more recent patterns. But if you knew that these were climate-based phenomena that could reoccur, then you might want to leave them in. But if you want to remove the outliers, a very simple way is to just perform a moving average. And as you can see, it drops out a lot of the spikes. But still, the data's a little bit spiky, but it's just a simple rolling moving average over, here it's just over 7 days. So you get rid of the short-term spikes that occur over 1 day or less. Then you can apply, another way is to apply exponential smoothing. So again, as we mentioned, it's the same technique of decreasing the weights to your past observations and more responsive to recent changes in the data. And that's the result. So not too different, but it's actually, as a side effect, because you're moving the data in this way, you actually remove missing values, because you're smoothing over a period, that you're running a window over the data. But yeah, you're still seeing some spikes there. You could then, another approach is to think about standard deviations and to just remove outliers based on where they lie on over a certain threshold. So you could say data points that have a Z-score. The Z-score is calculated by the mean of the data, so the data divided by its minus its mean divided by its standard deviation. And so you could say that any data points that have a z-score higher than 3 standard deviations, get rid of them. So if you do that, your data looks much more uniform. I mean, it isn't perfect, but in a sense, you've tidied up your data set. But yeah, I would say proceed with caution, because it depends what data you're looking at. If you're looking at financial, I don't know, volatility or something, you probably don't want to remove outliers because these highly volatile times can reoccur. But if you're looking at sensor data and you're pretty certain that this was a set of dodgy sensors or a different sensor supplier, then you might be justified in removing them. So yeah, that's another way to clean it up. So, okay, the last part of the sort of demo is actually applying, this should say number 4. I'm actually just trying actually a range of forecasting methods. I'll also demonstrate the library that I've developed over time. And what we're going to do, start with a simple data set. So it's very easy to load the data set in. You just say, I'll just call airline passengers. And it loads the data into this data set, what I've called a data set object. It gives you a bit of information about the data set. Tells you its time unit and seasonality, whether it's got seasonality or not, the number of columns you're looking at. So just one column is the number of passengers. So we saw this data set earlier. That's what it looks like. We can plot it. Oops. I think the kernel is just waking up. Here we go. There we go. That's what it looks like. We're plotting it here. So, sorry about the scale, but yes, that's a nice, very clearly multiplicative seasonal effect on a trend. So instead of taking our time looking at autocorrelation plots, why don't we just apply a grid search? So what we'll do is we'll train a model and then we'll work out the Bayesian information criterion. And that, as mentioned earlier, it determines like whether the model is statistically valid based on the number of parameters in the model. And the lower the value, the better the model. So we suppress a few warnings. We'll just run, I've just got a simple function, so you literally can run prediction equals ARIMA. So this is as easy as it gets. And then it runs through. And it's doing a grid search for you on the airline passengers. So unfortunately, in a live demo, it's a little bit too slow for us. But what it gives you is a prediction object. It tells you where the confidence intervals are in the data set and what type of confidence method is applied. It gives you the ground truth values and actually the predicted values. So then you can run a quick function called get metrics on your prediction, and it'll print all the accuracy metrics that we talked about. So mean absolute error, mean absolute percentage error, R squared, RMSE. So you have straight away an idea of how well your model's performing on ARIMA. And then again, so let's have a look at the performance. We just ran a grid search with our ARIMA model, but we're wrapping it in this STL forecast. So we're getting like fairly good performance on our ARIMA model, which has been curated to get rid of the seasonality trend before the model is trained on it. And that's what the output looks like. So it's fairly close to prediction, but it's not really capturing this increase in seasonality. What we need to do then is try, say, with SARIMA, which adds seasonality to ARIMA. So there, I don't need to wrap it in this STL forecast because SARIMA has seasonality built in. And I can apply a grid search again. So I'm comparing this Bayesian information criterion, and I get a slightly better result. So I plot that, and I'm even closer to the predicted values. So as you can see with this library, it's relatively easy to run predictions, get your metrics, so forth, on a certain data set. So try with a real world data set. Let's look at pollution in somewhere closer to home for some people. Bangalore. We look at air quality in Bangalore. We've got a few missing values, but we're imputing them, as mentioned earlier. We're applying this mice forest multiple chained equation approach. And there's our data all cleaned up nicely, put into weekly frequency. Got a various number of metrics in Bangalore. Let's do a prediction using our ARIMA module and get the metrics and see what we get. So running a prediction in Bangalore, what we see is that when we try and predict into 2020, certainly, there is, the model's not picking up the fact that there was a drop in pollution, possibly due to the COVID lockdowns, but still pretty good, guess of what's going on. And incidentally, this is the sort of recommended pollution level according to the Indian government. So you can see in Bangalore, there's often periods where you've got very high pollution, bad for your health. This is the recommended level by the World Health Organization. So slightly, the data is slightly higher than that. What we see in these predictions, as I mentioned, you've got the COVID effect. Let's try a more advanced model. Let's try profit. So just to run predictions with profit, it's a very simple run again. We just give the data set to profit, and then we get the metrics. The profit is actually, it understands, I've actually given it, I've told it geographies. I've said Bangalore, I've told it the state that Bangalore is in, and it's pulled out all of these holidays. I hope this is correct for Bangalore. If not, somebody in the audience can pull me up. But it's going to give us an idea of holidays because it's affecting human behavior, obviously. And this is included. So again, what we're doing is we're running a grid search on profit. So we're trying different values on profit, and it's a lot of output. But eventually you get your best configuration that's been determined after you've run many different versions of profit. You've got things like change points where they're occurring. You've determined that it's multiplicative seasonality. And then we've run the metrics module just to see how it's doing. We can plot the output. So there we're seeing, this is profits prediction. We're also seeing how the profit model sees the rest of the data set, not just around the prediction. So this is how profit is approximating the data in the training set in order to generate this prediction in the test set. So bear that in mind. The model is again just an approximation of the reality. So regardless of whether you're looking at the training set, it's not overfit training set. It's just generating the best possible result. So again, we're seeing like a big dip in 2020 compared to what the model is expecting. If we run a sort of more foundational model, like single exponential smoothing, again, you just run SES and then your data set. And that's, as part of this, we're performing some decomposition to feed to that model. Again, the prediction is a little bit higher, but not too far off the actual values. What we can do is run, we can try a different city. So we can look at Chennai, for example. If we run for Chennai, we get, again, the holidays for Chennai is best for the model. we run through again, and we get a prediction for Chennai's PM 2.5 levels in 2020. And this time the model is fairly close. There's a lot of variation. So that was running profit. So you're seeing slightly lower values than expected. If we run, say, with a more foundational model, Holt-Winters, Holt-Winters is very good at seasonality. If we run Holt-Winters, it's actually getting even closer, and it's picked up some kind of recent trend, probably due to the exponential weighting approach, and it's actually predicted quite well, despite there being COVID lockdowns, the pollution moving forward in that location. So it's not necessarily the most complex models are the most accurate. Can be the sort of, even the old models from the 1950s are still performing very well when you're talking about univariate time series. So bear that in mind. So that's the end of the demo part. I think we're close to running out of time. What I'll say is there's a lot of challenges with time series forecasting. We talked a little about data quality and quantity. We talked a bit about model selection and how you choose a parameter for your model. And we've mentioned the basics of splitting up your data. We've looked at some metrics cursively, and we've seen that the model doesn't necessarily have to fit precisely to the training data. In fact, you don't want it to overfit. And there may be many different factors in your final model selection. It might be you're deploying the model and you need very fast computational performance, and you're not so bothered about accuracy. Or it might be the accuracy is absolutely critical and you don't care how much GPU, CPU power you throw at it. Something to take into account. If people want to get involved with this library that I've created and contribute, then feel free. I've put the QR code up on the screen. So if you want to scan it, if you want to drop me a line, if you want to report bugs, try improvements, or submit a pull request. It's nice because you can run, as I showed, it's quite easy to run many different predictive methods, and you can get the outputs nicely formatted into a table. You can also compare multiple methods. So if you've got a particular data set, you can add it to the repo, or you can have a private version if it's private data, and you can compare. Here, for example, we're comparing many Indian cities against many different models, and you're sort of understanding which models perform best in which circumstances, in which city, and depending on the data quality. And of course, this library also performs imputation and sort of resampling of the data, cleaning it up. But yeah, welcome to provide feedback on this talk as well. Yeah, thank you very much for your attention. If you have any questions, drop me a line. I'm on LinkedIn or Twitter, or drop me an email either at Sahaj or at my personal email. That's it. Thank you very much, everyone. Do we have any questions?
I do have, friend. Just wanted to understand, like, how did transformer models perform as against other ARIMA methods or FBProfit?
Yeah, I haven't actually implemented them in this framework.
Because the reason why I asked so, because I tried implementing transformer models onto the time series analysis that I was doing, but
Yes.
it seems like it performs poorly. So what I went into certain Stack Overflow and Coda, what I found that it requires a lot of data to actually try to analyze the model.
Yeah, I think if your data is like 1 year or something, or 2 years, it's not good enough. I think if it's like hourly data and you've got months and months of it, then I think the transformer is very good, because it's going to pick up these patterns. Like when I was working with traffic flow predictions, we found that something like, but at the time we weren't using transformers, we were using LSTMs. That was the cutting edge at the time. It was pre-2017. But with LSTMs, we found that when there was something like a concert happening in the city or a car accident, a bad car accident on the motorway, we found that the LSTM was really good because it had observed this pattern like a long time ago in the past, and then it was able to see it again and then give us a likely scenario when the accident occurred. But if you're dealing with shorter term, like 1 to 2 years, then you're probably better off sticking with something like Profit or traditional method like Holt Winters if it's data related to weather, climate, or human behavior, which is very predictable on the aggregate. If you're trying to predict on the stock market, that's another story. So, yeah. Hopefully that answers your question, Suman.
It does, Frank. Thanks, man.
Hey, Frank, I think Chetan has a question. He has put it on message. I'll just read it on his behalf. He's asking a recommendation on the books and courses and also any helpful links to learn more on time series.
Yeah, sure. So what I would suggest, there's a good book by Benjamin Alffarth. So he's based in London and he wrote a book called Time Series. I can't remember what it was called, maybe Suman or Ravindra, I can look it up quickly. But we looked at this in our book review, and that's what inspired me to sort of get into this area actually, and just create this.
Just I shared. Just
yeah, Ravindra can share the link. Otherwise, there's some classic. I mean, if you really want to look at the classic books, there's a number of really classic texts. I can't remember the author names off the top of my head, but maybe I should put them into the repo actually in the README as recommendations. But thank you for that point. Yeah, I can definitely, if you drop me a line, I can definitely send you some links offline, as can any of my colleagues as well. Thank you. Any other questions? Yeah, Kaggle is really good. Oh, Ocean's already pitching in there. Very good. There's some good recommendations there. Right, well, if there's no more questions, we can wrap up. As I said, if you want to get in touch, please do so. Feel free to look at the repo, feel free to use the repo and contribute to it. Drop me a line if you want to contribute.
Thanks, Frank. It was really a great session, including the coding bit as well.
Thank you. Glad to hear it.
Thank you so much.
Thank you so much.
Thanks, Frank, for the session.
Pleasure. Take care, everyone. Thank you.